Hello everyone. In this video, I'm going to work out the fractional bandwidth of a quarter wave transformer matching network. So suppose you have a source impedance Zs and the low impedance Zl, and as you know it, what we need is a quarter wave transformer to uh, to form a matching network. The quarter wave transformer is basically a transmission line with the length equals to 90 degrees, and the characteristic impedance is Z of Q, where Z of Q is given by square root of ZL Z S. So this is the formula for the quarter wave transformer, and it sounds very straightforward, but there's a trade-off. One of the biggest problems of this matching network is it only works for one frequency. And I will tell you the bandwidth for this kind of network is surprisingly narrow, and you will not like it. And um, so let's take a look how we can work out the fractional bandwidth. To work out the fractional bandwidth, we need to know the refraction coefficient. So to know the refraction coefficient, you need to know the input impedance. The input impedance, as we know it, is going to be dq. So this is the general formula for input impedance of the transmission line. Now remember, theta here is pi over 2 only at one frequency. At other frequency, theta is not necessarily equals to pi over 2. So I will emphasize here, theta is equal to pi over 2 only at resonance. So in this case, we should not just straightforwardly substitute theta with pi over 2. If you do that, then it's not going to be correct. So now we need to find out the refraction coefficient, which is given by the difference, yeah, the Z in minus ZS. So we all know this. And what we need to do is substitute Z in into this formula. So if we do this, then it will be like this. And then the source, and then again here. So this is the so-called refraction coefficient. And I'm not going to put theta as pi over 2 because this is not our purpose. Our purpose is to find out the fractional bandwidth. So if you simplify this expression, then you will get uh, the Q VL plus J VQ square tangent and then VS VQ and then JVS VQ and then tangent theta. And at the bottom I got this. So it's plus side this time, eh? So if you simplify this expression, you will get you can group some like term. Say for example, this term has ZQ and this one is ZQ, right? So you can group some like term so that we can got like this. And similarly, for these two, we can extract the tangent term and play, and then what we get is, and similarly, at the bottom, we will get this. So we are almost done. Uh, so how are we going to further simplify this? So we can simplify this very easily. You can further simplify this, right? Eventually, what you will get is VL minus VS, VL minus VS plus J2 tangent theta, and then square root of VS VL. You need a little bit of algebraic manipulation in order to get into this stage. But don't worry, it can be done. So the next thing is to continue with this process. We are going to find the magnitude of the refraction coefficient. So it will be the magnitude of the numerator, and at the bottom you will be assuming that the low impedance and the source impedance is a real number. So what we have here will be square and then plus 4 tangent square beta and then VS VL. And then you just take the square root. And now there's a trick. What we need to do is to divide the top and bottom by VL minus VS. So what we get here is VL minus VS plus 4 tangent square beta VS VL. So it will be VL minus VS. Remember, square. Yeah, because it's inside the square. I think there's some problem here. I think here is pass. So in this case, pass. So the final step is to simplify this. So I'm going to do it for you. 1, and then here you need a little bit of trick. You need to expand this first. So if you do a little bit of simplification, I'm going to clean up the whiteboard. So we are going to continue from here. So in this case, according to here, you get I'm just copy it. I've just copied it. So you get this. So what I'm going to do now is to do a little bit of algebraic trick right here, and instead of having, I will put z as the, I will just rearrange this in this manner, and then for so this is what we get. So finally, and this guy here is VL minus VS, and this bit here will become 4 1 plus tangent square is secant square. So what you get here is 1 plus 4 and then secant square. So I think you are clear now. And after going through all this hustle, we finally get the clean expression that represents the magnitude of the refraction coefficients. And from there, you try to find the meaning. Now, first of all, before going forward, I will tell you what happened if we plot this graph, plot the magnitude of refraction coefficient against theta. You will get this. You will get something like this. You get something like this. And here is pi over 2. Exactly pi over 2. And you can also translate this into frequency. Remember, beta is equal to beta L, and beta L is 2 pi f, and then velocity, and then L. So L here represents the frequency. No, L doesn't change, velocity doesn't change, uh, pi doesn't change, 2 doesn't change. The only thing that changes is beta and frequency. At different frequency, the value of beta is different. When frequency is at right at resonant frequency. So this one, right, is corresponds to this beta pi over 2 is the frequency at resonance. So what about the other? It depends on the value of the magnitude of the refraction coefficients. If you define this as a tolerable refraction coefficient, then we will find two values here representing theta. And if you do this, this means when you do this, you will be able to solve this equation. For and then secant square. And this equation will give you two values. One is beta m1 and the other is beta m2. It doesn't matter which one you are going to get. This is going to will end you up with a length corresponding to the frequency. And for as far as frequency is concerned, this one will be f of m1 and this one will be f of m2. Yeah, because of this. So, but our ultimate goal is to work out the fractional bandwidth. The fractional bandwidth, by definition, is the bandwidth corresponding to this length. So delta F over F naught. This is the definition of fractional bandwidth. And what is delta F? Delta F is this length. And what is this delta? So it's difficult to find, but what we can do is we just pick one value, say beta of m. So beta of m and then minus beta naught. Beta naught and then times 2. So this is the value that you expected to get for correspond to the delta F. And what about here? This is beta naught. Beta naught is the value of beta L that give rise to the resonant frequency. So this is what is the reason why I write in this manner. And beta L naught, according to here, is pi over 2. And beta m will be found out later. And beta naught pi over 2 and then times 2. So what we get here is 2 pi beta m four pi over m divided by pi and then minus 2. But theoretically, this one will give you a negative value. Most likely you will need to find the absolute value. Because most likely beta m will be this one. Okay, so we are going to do this. So let's say we get this. So this is the fractional bandwidth. Well, what is the value of beta m? Beta m can be obtained from this formula. So let's do some rearrangement for this equation. If we take square for both sides, we get beta m square and then 1 over 1 minus 4 and then secant square is cosine square, 1 over cosine square. So beta m. So this is beta m. And it's not difficult for us to find the value of theta m. What we just need a little bit of algebraic expression. So this one move to the left. Uh, so uh, let's just do some cleanup first. It's a little bit messy. Or just continue. You just continue, yeah. We just need to continue. Yeah, just continue. So from here, theta m uh, cosine square is theta m square. Actually, we can take square out. So if you do it very carefully, you will get this. So this is the value of theta m. So what we need to do is substitute this into this. So as a result, what we can get here is fractional bandwidth equal to 2 minus 4 over pi, and then cosine 1 minus cosine square, and then so this is what you are going to get for as a formula for the fractional bandwidth. So I hope this is clear enough to you. Uh, the value of delta F divided by F naught is equals to 2 minus 4 over pi, and then A cosine, and then this trunk of expression. Uh, okay, I presume it's pretty clear now, except that here is a little bit messy. I solved the value for cosine theta m from this equation here. And then from here, I substitute the value of theta m into this formula, and this is how I get. And this is the so-called fractional bandwidth for one quarter wave transformer. Okay? If you have any question, please leave your question to the comment section. Thank you. Bye-bye.